In this lesson, we are going to start talking about a method called using confidence intervals. And we're going to use sample data to generalize about an unknown population. And just a quick recall, if you think back to the beginning of the class, remember there were two branches of statistics. There was descriptive and there was inferential. Up to this point, we've been doing descriptive, where we've been collecting data, organizing it in charts and things like that. Now we're going to actually use the data to draw conclusions about the population. And so now we're entering into the branch of statistics that's called inferential statistics. So we're going to use the sample data to make an estimation about the population parameter. Now, when we do this, there are different methods to use based on the information that's given and based on the situation. What we're going to study in this section is using the normal distribution. That's the method we're going to use in this section. And we can use that when we know the standard deviation of the population. Now, that doesn't happen too often in real life that we know what the standard deviation is of the whole population. But it does happen, just not that often. But this is the method you want to use if you know what the standard deviation is. Okay, so when we create a confidence interval, basically what we're doing is we're setting up an interval that we are saying that we're a certain level of confidence that the population parameter is going to lie on that interval. So there's going to be some wiggle room because we can never figure out exactly, and we can never be 100% sure that it's actually going to be on that interval. But what we're going to do is we're going to set up the interval using our knowledge of normal curves and areas under the curve. We're going to look at what's called the point estimate. So that's going to be in the middle, the mean, and then we're going to add and subtract our error. So when we take 10 plus the error and 10 minus the error, that creates that lower and upper bound to create our interval. And then we can say we're pretty sure that the population parameter is going to lie on this interval. So as we go through some examples, I'm going to introduce some new vocabulary to you. So far, what has been introduced is the word point estimate, and that's going to be the sample mean or proportion that we're going to use to create the confidence interval. Okay, now I'm going to show you how to do this by hand, and I'm going to show you how to do it on the calculator, and you can choose the method that you want to use. If you're going to do it by hand, these are going to be our steps, okay? And I'm not going to get into a full-blown example at first. What I want to do is I want to first walk you through a simple, very basic one where a lot of the information is already given to you so that you get the concept. And then we'll work up to harder ones, and I'll show you how to do it on the calculator as well. So we're going to start off with a very basic, simple one. It says, suppose we have collected data from a sample and we know the sample mean, but we do not know the mean for the entire population. So we're trying to estimate the mean of the entire population, but we know the mean of the sample. The sample mean is 7, and the error is going to be 2.5. So what we're going to do to create this interval, and by the way, this here is notation for error bound for the mean. That's basically just a fancy way of saying that's going to be the error. Okay, so to create the confidence interval, I imagine that my mean is 7 in the middle. And then I want to give some wiggle room of an error of 2.5 because, of course, we're not 100% sure what the population is going to be. We're just trying to make an estimate. If the error is 2.5, I'm going to add 2.5 and that's going to be my upper bound for the interval. And then my lower bound is going to be 7 minus 2.5. So my confidence interval will be 4.5. That's what I get when I take 7 minus 2.5. And then my upper bound is going to be 9.5 because I take 7 and add 2.5, and we get 9.5. So this is my confidence interval, and sometimes you'll see it abbreviated CI. So this is what we're estimating that the population mean is going to fall somewhere between 4.5 and 9.5. We have different levels of confidence depending on how wide or how narrow our interval is. If we're going to assume that this area that's under the curve between those two values is 95%, then we would call that 95% confident, or a confidence level is 95%. We would say that we estimate with 95% confidence that the true population parameter, or in this case specifically we're talking about the mean, so let's put that in there. The true population mean is between 4.5 and 9.5. So whenever you go to interpret a confidence interval, you always want to use this as kind of like a template. You always want to say, we estimate with, and then you put in the confidence level. And then you say that the true population, and then you put in whether it's the mean or the proportion. In this case, we're talking about the mean. And then you put in is between, and then you put in what your confidence level is. Suppose scores on exams in statistics are normally distributed with an unknown population mean and a population standard deviation of 3 points. A random sample of 36 scores is taken, and it has a sample mean of 68. We want to find a confidence interval to estimate the population mean for exam scores. And that's for all exam scores, because we're trying to find the population mean or estimate the population mean. Part A says find a 90% confidence interval for the true population mean of the statistic exam scores. So this is the picture that we have. We have our point estimate. That's our X bar, our mean of the sample that we're going to use to help us estimate or create our confidence interval. And it was told to us that this value was 68 in the problem. Now, we also know that we need to have a 90% confidence interval. So we want to come out in such a way that 90% is under the graph between those two values. So I'll call this lower bound and upper bound for our confidence interval. So that's what we need to find. Now we do know, because they gave this to us in the problem, that the population standard deviation is 3. In real life, that usually doesn't happen, but when it does, that's what this whole section is about. How can we create a confidence interval for the population mean if we do actually know what the standard deviation is for the population? So in order to use this method that we're using in this section, we have to know what that population standard deviation is. Okay, so in previous section, when we were talking about the central limit theorem, when we talked about pulling different samples, and we were finding the distribution of those X bars, our standard deviation for that was the standard deviation of the distribution x divided by the sample size. That's what we're going to use here for our standard deviation of this distribution. But then we need to use that to find out how far out we come. If this is the standard deviation for the sampling distribution, what we need to know is how many standard deviations it comes out in either way. Because if we know it comes out 2 standard deviations, and we know what the standard deviation is, we can just multiply it by that value and we've got it. So what we're going to do is we're going to figure out how many standard deviations we come out in either direction. And that is why we learned about z-scores. That's going to help us figure it out. If I know that 90% is in the middle, it's the middle 90%, and I want to figure out what these tails are so I can use inverse norm to find out what that z is. So 100% is in the total area under the graph. So I know that 10% is left over, and then I split it up between each wing. So each wing is 5%. So I can find my inverse norm and find my z by doing inverse norm. I want to find my value of z, and we're doing it for a percentile of 5%. So I'm going to put in 0.05. Then I'm going to put in, this is for the standardized, so I'm going to put in 0 and 1 for my mean and my standard deviation, and that will tell me how far I am out in terms of z. When we do that, we're going to get 1.645. So that means I'm 1.645 standard deviations out in either direction. And our value of z, when it's indicating it for this confidence interval, that's called our z critical. And it has a little c down here to indicate that that's our critical value. That tells us the cutoff point. And then we take it and we multiply it by the standard deviation of the population divided by the square root of n. We found that our z critical is 1.645. Then we multiply by the population standard deviation, which is 3, over the square root of the sample size, which is 36. Then when we multiply that out, we're going to get 0.8225. That's going to give me my error. So that's going to tell me how much I come out this way and how much I come out this way. So now I can use this to find my confidence interval. So my confidence interval is going to be what I get when I take 68 minus 0.8225. That's going to give me my lower bound. And then I'm going to take 68 plus 0.8225. That's going to give me my upper bound. Okay, for my lower bound, I'm going to get 67.1775. And for my upper bound, we're going to get 68.8225. So what this means is, if I were to write an interpretation, I could say that I'm 90% confident that the population mean is going to lie between 67.1775 and 68.8225. Now, we could have actually gone back. Let me change this. I'm going to show you a trick. I'm going to erase this. So when I used inverse norm there, I was just trying to find my critical value of z. So how many standard deviations I came out when I'm looking at the standard z-score. I could find this directly by putting in my x bar, our sample mean, and then put in our standard deviation, which was 3 over the square root of 36. And when you do that, you get the same thing, but I would just get my lower bound. So that gives me the same answer directly as my lower bound. Now, if I wanted to find my upper bound, there's a couple different things we could do. we could go ahead and use symmetry to find what the upper bound is. So I find the difference between 68 and 67.1775. If I find that difference and then add it to the other side, that would give me my upper bound. Or I could just go back and do inverse norm again, but I would just have to change my percentile. So if I did it that way, I would have to look at a new percentile. If I want to find this value here that I just highlighted, I would put in 95 to the left, and I would put in 0.95 for my percentile. And I should get 68.8225 for that, which would give me my upper and lower bounds. So you can do it with the calculator using inverse norm and doing different steps. And then one more way I'm going to show you how to do it on the calculator that actually does everything in one step. It makes it so much easier, but I wanted to walk you through the different ways that you can calculate this to help you understand where these numbers were coming from. So let me go ahead and pull this up on my calculator and I'll walk you through it. Directly all in one step on the calculator, and this is what I recommend that you actually do, but what you're going to do is you're going to go and hit the stat button. And then you're going to arrow over. We've used the edit menu. We've used the calculate menu. Now we're going to arrow over to the test menu. We're going to scroll down and we're going to go to number 7 and we're going to find a Z interval. Z stands for the standardized normal curve. So that's why this is labeled a Z interval, because we're using the normal distribution. Okay, so because we know what the population standard deviation is, I can use Z interval. I'm going to hit enter. And then what I'm going to do is I'm going to enter in, see this is highlighted in overstack. Since I know what the values are and they were given to me in the problem, I'm just going to use the stacks option. So make sure that says stacks there. And then I'm going to go down and put in my information. The population standard deviation that was given to us was 3. The X bar, that's the sample mean, that was given to us as well. That was 68. 36 was our sample size. And we want a confidence level of 0.90. You always put in your confidence level as a decimal, not as a percentage. And then I'm going to go down and I'm going to hit calculate. And as you can see, it gives me the interval right here. It gives me the lower bound is 67.178 and the upper bound is 68.822. So it does it for you all in one step. So once you get familiar with where the numbers are coming from and why we're doing it this way, the calculator makes it much easier to do it all in one step. Okay, now we are going to go ahead and find this for the 95% confidence interval. So we have our mean, which is in the middle, which is our 68. That's our X bar. Remember, our standard deviation is going to be 3 over the square root of 36. And now that we want to be 95% confident, we're going to have in the center 95% for our percentage. Which means when I go to find my upper and lower bounds for that interval, my wings, that percentage that are in my wings are going to change. So if the full graph covers 100%, then that means in the 2 wings, what's left over is 5%, and I have to divide it between the 2. Using symmetry, this I know is going to be 2.5%, and this will be 2.5%. So when I go to calculate my inverse norm to figure out what that value is, I'm going to put in that my percentile is 0.025, then my mean is 68, and my standard deviation is going to be 3 over the square root of 36. When I do that, I'm going to get 67.02. So that's this number here. Okay, now we're going to do the same thing on the other side. But I got to change my percentile because now I'm looking at this one here. So I got to take 95% and add it to the 2.5% because that's everything to the left. So my percentile now is going to be 97.5. So I'm going to put it in as 0.975 as my percentile. Think 68, and then, whoops, and then 3 over the square root of 36. When I do that, we get 68.97999. So I'm going to round it to 98. The other way that we can do this is using symmetry. Once we get one value, whether it's the upper or the lower bound, we can use it to find the opposite endpoint, because we know that the difference here, that's going to be our error. That's going to give us our wiggle room that makes our confidence interval. So if I know that this value right here is 67.02, I can find the difference between 68 and 67.02. If I find that difference, that's going to give me 0.98. So I know that my error is 0.98. But that's going to be the same on this side too, because it's symmetric. So to find that other endpoint, I can take 68 and add my error, which is 0.98. And that gives me 68.98, which is what we got when we did it using inverse norm. Because of the symmetry, you can do that. Lastly, you can use the confidence interval function on the calculator. Remember, for this section, when you know the population standard deviation, you use the interval. So you could put all that information on your calculator and you should get that you have a lower bound of 67.02 and an upper bound of 68.98. So let's go ahead and practice that. Okay, so to find that interval function on your calculator, we're going to hit the stat button and we're going to go over to tests. And then we're going to come down and we're going to find our confidence interval using the normal distribution. So we're going to be using our z's. I'm going to come down and find the z interval. Because we know the values, we're going to use stacks. And in a minute here, I'm going to show you how to use the data option on this. Okay, our standard deviation for the population is 3. Our mean is 68 for the sample. All of this is the same. The only thing that's changing is that we're doing this for a different confidence level for 0.95. So I'm going to go ahead and put that in there, that we're changing our confidence interval. I'm going to hit enter, and it's going to give us the same thing we did when we used inverse norm. So we got 67.02 as our lower bound and 68.98 as our upper bound. And when we use that interval function on our calculator, it gives it to us at once so that we don't have to do the 2 steps of inverse norm. So because we have with the 95% confident interval, our error would be wider. It would be bigger because that distance from the mean is bigger. So that would give us a higher probability that it would fall on that interval, which gives us more confidence, which is why the confidence level goes up. So here's a summary down here that gives you some, like a concept check. So the increasing of the confidence level increases the error, which makes the confidence interval wider. We just saw that in the picture, and then that works in reverse. If you decrease the confidence level, you decrease your error, which makes the confidence interval smaller. Okay, now let's just make a quick calculator note here. So again, I'm going to stress this a lot because this is usually where students get stuck. When we know the population standard deviation and we are trying to estimate the population mean. Then we use z-interval. Or you can use inverse norm, but you'd have to do it in multiple steps that way, but it's fine, it works. To get to z-interval, you go to stats, then to tests, and then choose z-interval. If you know what the values are and they're given to you in the problem, like the population, standard deviation, and the mean for the sample and all that information, when you do the interval, the z-interval function on the calculator, you want to choose the stats option because you're just plugging in the values. Now, the other option, if you have the data and you have to figure out the stacks yourself, then you choose the data option and it will figure it out for you without you having to do that in a whole nother step. So let's walk through an example of that. In the next example, it says a specific absorption rate, SAR, for a cell phone measures the amount of radio frequency energy absorbed by the user's body when using the handset. Every cell phone emits RF energy. Different phone models have different SAR measures. To receive certification from the Federal Communications Commission, FCC for sale in the United States, the SAR level for a cell phone must be no more than 1.6 watts per kilogram table that shows the highest SAR level for random selection of cell phone models as measured by the FCC. Wow, that's a mouthful. All right, so we have all the different models, and then we have the SAR measurements. And down here it says find a 98% confidence interval for the true population mean of the specific absorption rates for cell phones. And we're going to assume that the population standard deviation is 0.337. Now, in order to find a confidence interval, we need to know what the sample mean is, and then we have to plus and minus the error so we can get our interval. So, but they don't give us what the sample mean is. However, we can figure it out by putting all of these values in the calculator in our list and finding the sample mean using one variable stacks. That adds an extra step to the process. However, we can do it. We can actually go ahead and go straight to finding the confidence interval by using z-interval, like I showed you in the previous example, but instead of picking stacks where we know what the statistics are, we know what the sample mean is, we know all those values, we plugged them in. But now we have to actually calculate it first. But since we know what the data values are, we can choose data instead of stacks. And what we can do is we can put all of these values that we have here in the table, we can put them in one of our lists and tell the calculator to base the statistics off of that list. And then all we have to do is just use the z-interval, and then the calculator does the work for us. The only thing is we have to just be really careful and make sure we put those data values in correctly into our list. So let me show you how you can do that. All right, what we're going to do is we are going to go to the Stat menu. We're going to go to Edit, and we're going to enter in all those data values in the list. There should be 30 of them. So take a minute, pause the video, and go ahead and enter all of those in, and then unpause when you're ready. Once you have all those values in there, you're going to go ahead and hit Stat again, and we're going to arrow over to Test. I'm going to go down and choose Z-interval. Now, I know that we're using a Z-interval because we know what the standard deviation is for the population. So I'm going to hit Enter on Z-interval. And now this time, I'm going to hit Data. Before we were using stacks, because when I hit the Stat button, I can enter those values here, okay? But if I don't know what those values, but I have the data, I could go over and hit enter on data, and I just tell the calculator what list it's in. I put mine in list 1. You go ahead and put in your standard deviation, which the problem told us was 0.337. And then you go down and you put in your confidence level, and then you hit calculate, and it will give you your interval. And it calculated the mean for you at the same time. The sample mean is 1.0237. And then here's the sample standard deviation. And then here's our sample size. So our lower bound is 0.8806. Our upper bound is 1.1669. So now I'm going to write down our confidence interval and write down our interpretation. So when we looked at the calculator, our lower bound was 0.881 and our upper bound was 1.167. So my interpretation would be, since we're doing this, what was our level? 98. Okay, so we have the true SIR mean of the population of cell phones in the US. That's what we're talking about in this problem. So that's still part of that fill in the blank. And that is between, and then our lower bound we have is 0.881, and our upper bound is 1.167. And then, of course, we got to put in our units walks per kilogram. So just remember, when you're writing your interpretation, you're always going to start with, we estimate that the true, and then fill in the blank with whatever it is that you're looking for in the problem. And then you put in is between, and then you put in your lower and your upper bound, and then you make sure you put your units at the end. And then that's all you really have to do for these. The calculator does the majority of the work for you. When we get into the later sections, it's just going to be a matter of trying to find which calculator function we're going to use for that interval. In this last example, I'm going to show you how you can calculate the sample size. Now, we need to know that if we're trying to work backwards. This happens a lot when researchers want a specific margin of error. They have to have a certain sample size. So if you want to find a certain sample size that will work for your confidence level and for your interval, then what you're going to do is you're going to use this formula to find what that sample size needs to be. The book uses EBM for error bound for the mean. But if you ever see me write it like this, because I grew up using this notation, E is the same thing as the EBM. It's just the error. Okay, you're going to take your z-score and square it, multiply it by your standard deviation squared, and then divide by the error squared, and that will give you your sample size. So the example reads, the population standard deviation for a Foothill College student is 15 years. If we want to be 95% confident that the sample mean age is within 2 years of the true population mean age of the Foothill College students, how many randomly selected Foothill College students must be surveyed? So it's asking for the sample size. How many must be selected? What does my sample size need to be if I want a 95% confidence level? If I want the center to be 95%, I need to figure out what these z's are on either side. I need to figure out what these z's are so that we have that 95 confidence level. And so we also need to know what the error is, but that is given to us in the problem. We want it to be within 2 years. That's my plus or minus. That's my error. So really the only work other than reading the information from the problem is finding out what my value of z is, so that I can plug everything into my formula. Now we can use inverse norm to figure this out, because I know that if 95 is in the middle, then there's 5% left over from 100, and I have to divide that between my two wings. So each wing is going to be 2.5%. So I'm going to use inverse norm. And I'm going to put in, for my percentile, 0.025, because we always put in the percentile, which means the percentage to the left. And then I'm going to put in that my mean is 0 and my standard deviation is 1, because we're talking about the values of z's, not the raw scores, but the z's, the standardized scores. So my mean is 1, or my mean is 0 and my standard deviation is 1 when we got it standardized. So when we put that in on the calculator, you're going to get that the value of z is negative 1.96 over here, which means over here it's going to be the same thing based on symmetry. So we're going to put in, for z, for this formula, you just put in 1.96. It doesn't matter if you put the negative or not, because when you square it, it doesn't matter. The sign will disappear if you put in a negative, because we're squaring this. Okay, so to find my n, I'm going to put in 1.96 squared. That's my z squared. Then I'm going to put in my standard deviation, which was given to be 15. That's right here in the problem. And then also we were given in the problem the error, even though it didn't explicitly say the error is, we can figure it out from the wording of the problem that it's within 2 years. So that's my error. That's my give and my take. So I'm going to put in parentheses 2 and square it here. Now, when we put all that in on the calculator, we have 216.09. And we're going to bump up. We always, in this case, want to bump up, because we want to ensure that the sample size is big enough for this to work. So if I round down, it might not work. So we always bump up. So we're going to say that n is going to be 217. So we need 217 students at least in the sample in order for us to have a 95% confidence level. So we talked about how we find the confidence interval, and then I showed you how to do it on the calculator. Then we talked about how you can find the error if you're doing it in reverse, where you know what the confidence interval is, but you're trying to find the error. And then I showed you how to use this formula here to find the appropriate sample size so that you can determine your interval at a certain level of confidence. In the next section, we're going to talk about what to do if we don't know what the population standard deviation is.